Hi, everyone. Before we listen to Professor Gerd, I just want to bring to everyone's attention just 2 points. And I think those 2 points will sort of help us to really sort of appreciate Professor Gerd's presentation very well. So today's this deep learning centric paradigm advances in AI is all about scale, bigger data sets, larger models, more compute. But have you ever thought about the consequences of this big scale? The recent, some of the studies are showing that the carbon footprint of training just a single large language model is around 300,000 kilograms of carbon dioxide. And if you really go a bit more deeper into the root cause of this carbon footprint of AI, we realize that a large supercomputer uh, you know, uses up about 5 megawatts of power. That's about 250,000 more power than what a human brain uses, which is just 20 watts. So is bigger always better? Is computer always superior to the human brain? The second point I want to bring in is Professor Gerd is going to speak about heuristics. And immediately, a lot of us would say, oh, I've heard of heuristics from a lot of behavioral economists. And behavioral economics have told us that heuristics are bad. We should keep them away. And I can assure you, Gerd has a very different perspective. For that matter, a very contrarian perspective to what behavioral economics have about heuristics. And it would be lovely to hear what he has to say. So, Professor Gerd, we're eagerly waiting to hear from you.
Thank you so much. How to make better decisions, how to deal with risk and uncertainty. Our society is split about what the answer is. So on the one hand, the idea is complex algorithms, big data, just increase volume, velocity, and variety and measure what correlates with what. On the other hand, complex financial models missed the financial crisis of 2008, and big data analytics predicted in 2016 that Hillary Clinton will win the US presidential election by a large margin. So can we really trust only on data and analytics? My general answer will be, no, we need both. We need the capacities of the human mind that have been evolved over centuries, over millions of years, and the capacities of big data and complex analytics. So let me start with a quote by one of the most smart peoples on earth, Albert Einstein. He was saying, the intuitive mind is a sacred gift and the rational mind is a faithful servant. We have created a society that honors the servant and has forgotten the gift. So what I'll invite you now to a voyage into the research at the Max Planck Institute for Human Development in Berlin on heuristic decision-making. I will explain what a heuristic is. I will make the point that heuristics are necessary tools to make decisions under uncertainty. And then I will give an example about a heuristic, how it works and when it works, and then move into several examples about how one can make decisions in the world of business and finance, often by just relying on a single data point or no data at all. and nevertheless be better than big data and very complex algorithms. And the reason behind this is that the more complex your model is, the more you will overfit the past. And if the future is not like the past, you're not doing as well. And I will end in explaining the rationale behind simple heuristics, and also when situations are where less is more. That's the plan. Are you ready? Then let's begin. So the basic distinction I would like to begin with is that between risk and uncertainty. It is a distinction that is too often overlooked. A situation of risk is one where we have perfect knowledge about all future states of the world, their consequences and probabilities. It is basically, if you play the roulette, nothing unexpected can ever happen. You know everything. And that's where most of economic models are made for. It's the Arrow de Breu, or in finance, the Merton Markowitz agenda. And this is also a world which is stable, where tomorrow is like yesterday, is the best world for big data and complex algorithms. So in astronomy, big data is highly successful because the movement of the planets is highly stable relative to our short lives. But that does not extend to situations of uncertainty. Uncertainty is most of our real world, where the future states cannot be perfectly foreseen. That's how to decide whom to hire, whom to fire, where to invest, or whom to marry. Unexpected things can happen. In these situations where one cannot calculate the risk exactly, more is needed. And the two tools I will talk about are heuristics, which are robust, often called fast and frugal heuristics, because they allow quick decision-making, and also intuition, here the unconscious use of heuristics. So let me start with an example from sports. The example will make clear that a heuristic is nothing irrational, as much of behavioral economics still claims, but it is an smart policy to make decisions under uncertainty. So the example is about sports. So who of you plays baseball, or maybe cricket in India, or soccer? So imagine a situation where a ball comes in high, and an experienced player knows where to run to catch or stop the ball. How does he or she know? Now, there are two theories. One is, it's a complex problem, we need a complex solution. And the complex solution might be to calculate the trajectory of the ball. Have you ever calculated a trajectory? It goes like this. And the problem is not calculation, it's estimation. We can calculate today almost everything, but not estimate. So, for instance, to estimate alpha, the original angle with which the ball has been kicked or thrown. And you may also notice that I have left out a few important variables from the equations just to make it simpler. There's no wind, there's no spin. Nevertheless, how else could a ball player catch a ball? Now, experiments with experienced players show that they don't calculate trajectory, consciously or unconsciously, but rely on a set of simple heuristics. And I show you the simplest one, which works if the ball is already high in the air. It has three parts. The gaze heuristic tells the player, fix your gaze on the ball, start running, and adjust your running speed so that the angle of gaze remains constant. This player here does exactly that. Watch the player. The angle of gaze will remain constant. So it's running in a way that the angle of gaze is constant. What happens? The player ends up exactly where the ball is coming down. Do you want to see it again? The important thing is that the player can ignore all the variables in the trajectory equations, and also those I left out, and focus only on a single variable, the angle of gaze. And you can see that this heuristic is faster than trying to calculate and estimate. It is more reliable because you don't make the estimation errors. And also, it's transparent. You can teach novices to use a heuristic. The players usually use these heuristics intuitively. That is, they know what to do, but they cannot explain. So intuition means that you have an idea comes up here, and you think that's what you do, but it's not in language. You can't explain it. In our research, we study experts, like ball players, but also other experts, and work out the heuristics they use, make them explicit in order to teach others to use this consciously. Here's an example for the gaze heuristic. You may remember the miracle on the Hudson River. A plane started, took off in LaGuardia Airport, and a few minutes later, something unexpected happened. A flock of Canada geese collided with the plane. And the jet engines are built in a way that they can digest birds, but not Canada geese, as they are too fat. And the unexpected thing was that they flew in both engines, which shut down. The pilots, Sullenberger and Skiles, immediately turned around and had to make a decision of life and death. Will we make it to another airport? Or do we have to take a risky option like going into the Hudson River? How did they make the decision? Did they estimate and calculate the trajectory of the sailing plane? No. They used the same gaze heuristic as the player. In that case, the pilot looks through the windshield in the cockpit and focuses, say, the tower of the airport. And if the tower goes up in the windshield, then you will not make it. You will hit in before. And that decision can be made within seconds, and it's safer than all kind of calculations, which always may have errors. And at the end, all the people were saved by a combination between simple heuristics and, on the other hand, checklists and other things which are not of heuristic nature. So the general point is, in many situations, we arrive at the best decisions if we combine smart heuristics that are often intuitively used and the data that we have. So the same procedure, namely studying experts, extracting heuristic, and teaching these novices, can be used for leadership. Many leaders have what I call an adaptive toolbox of heuristics and are intuitively able to pick the right heuristic for the right situation. What you see here are 6 leadership heuristics that have been found in deep interviews with CEOs from the top US companies. And the examples here are either about people, how to deal with people, or to deal with strategy. So, for instance, hire well and let them do their job. That's a heuristic that creates a climate in a business of quality, hire well, and trust, let them do their job. For instance, many universities have forgotten these heuristics, and I have seen too often that committees that hire new colleagues don't put in too much work, don't read the papers all the time, but then control the new colleagues very closely after every year and so on. The Max Planck Society, where I work, is different. A director is hired and maybe a long search, often too long, but then trust. Let them do their job and let innovation happen rather than fine regulated. And I give you another example from strategy. For instance, take the last one. Don't buy financial products you don't understand. If before 2008, everyone on both sides of the Atlantic, so Europe and the US, would have followed this heuristic, the financial crisis would not have happened as it did. And much of the problem was, not the only one, buying products that are not transparent, and you buy it because everyone else buys it. That's this. So let me go on here and explain our research program at Max Planck. So it has 3 questions. What is in the adaptive toolbox of a leader, of a person, of an institution? And that are the heuristics, they're building blocks. Building blocks can be used to recombine heuristics to make new ones. And evolved capacities would relate to the evolved capabilities of the human brain, such as the ability to keep your eye on a moving ball against a noisy background, which is still difficult for a robot. That's the descriptive question. Then there is a prescriptive question, namely, can we identify the situation where a given heuristic works or fails? This question is new because in behavioral economics, there was this wrong idea that heuristics are always second best. You never had to ask this question. And some kind of logic or expected utility maximization supposedly gave you always the right answer. That's a big error. These logic, probability theory, expected utility maximization work in situations of risk, but not under uncertainty. And finally, there is an engineering question. So how to create environments or heuristics that help people to improve decision-making. For instance, with the Bank of England, we work on designing simple strategies to estimate whether a bank is volatile or not, is in danger or not, which work under uncertainty better than the highly complex problem. So let me give an example of each to illustrate the research. And the first one is about one reason decision making. I chose that because that's particularly challenging. Can we really make with one data point good decisions? So Herbert Simon, on whose work I'm building, he asked the question, how do human being reasons when the conditions of rationality postulated by the model of neoclassical economics are not met? In short, when we are not in a situation of risk, but under uncertainty. And let me give a first example. Assume you have a company which has hundreds of thousands of customers, and you want to know or predict which of your customers will buy again. So in order to not waste sending special offers to customers who will never buy again, or catalogs or whatever. This is a difficult problem. It's a problem under high uncertainty. There's no optimal way to do this. But still, you can do it better or worse. So 2 colleagues of mine, professors of marketing, they observed that managers in 3 companies relied on a heuristic to predict which customers should stay in the customer base and which should be eliminated. Yet they had learned that rational decision-making means using complex models. So we have the same situation as with the ball player. Shall we find a complex solution to this problem or a simple one? So I'll show you first the complex solution. Now they were favoring, that's the Pareto negative binomial distribution model. I'm not going to explain it. Just look at it and you will be impressed. The what I had observed is that the managers, experienced managers, relied on a simple heuristic. The heuristic is called the hiatus heuristic. If a customer hasn't purchased within 9 months, classify as inactive, otherwise of active. It's a one clever reason heuristic. So the 2 colleagues now were empirically minded and tested. They wanted to convince the managers that it would be better to rely on the complex model rather on one reason. Then could it be that one reason is better than more? So they set out a test. And here's the result of the test. There were 3 companies, an airline, an apparel, and a CD Now. The heuristic, the hiatus that the managers used were 9 months here, 9 months in the apparel, and 6 months in the CD Now. There's a more turnout. So what you see here is the correct predictions. The Pareto negative binomial distribution model got 74% correct predictions, 75 and 77. The simple heuristic got 77 more for the airline, even more for the apparel, and equal for the CD Now. Here at least one doesn't have to expend time and effort for data collection and processing. What you see here is what I call a less is more effect. Less is more means that there are 2 types of models. One is complex, the other one is simple. And the simple one is a subset, has a subset of the information, no extra information, just a subset. And by digesting less information, it makes better predictions. The reason is known as overfitting. So the Pareto model has 4 free parameters. It fits on data, but this is not a stable world, so it overfits. The simple heuristic, if the hiatus is fixed, has 0 free parameters. It ignores all past data, just goes for the hiatus, and thereby it makes better predictions. So when that was published, the question was, yeah, maybe the Pareto negative binomial distribution model isn't so good as it was thought to be. So what about heavyweights? Say logistic regression, other types of these models, and or even machine learning models. So the best heavyweights of that. And it's just 3 companies. So my own researchers and I joined these 2, and we had a data set of 35 companies, and where we took as competitors to the simple heuristic random forests, which is one of the most sophisticated models of machine learning, logistic regression, and another of these stochastic models. Just look at the left side. These are now an average over 35 businesses. You see again, the Pareto negative binomial model doesn't do very well. This other stochastic model even worse. Logistic regression does better. Random forest is about the same, but on average, the simple heuristic achieves better predictions than all the others. Then we ran another experiment where we used 25 different other repeat problems like healthcare. Will a patient who is released from the hospital come back to the hospital within a certain time? So that's the question. Or weather. Will there be another tornado in a region where already one happened, or another terrorist attack? And what you can see, the hiatus, so just relying on recency, if something happened recent, it will happen again, is an extremely powerful cue. And it outperforms again, on average, all these machine learning heavyweights or standard economic models or the marketing models. So this is an example of another less is more effect. And I chose it to illustrate that in very complex situations, often if you can identify a good heuristic, you do better. Now the next question is, in what situation is that the case? It is not always the case that complex is better than simple or simple is better than complex. The real and the interesting question is, can we identify the situations where no linear model can ever beat a single, a heuristic with a single reason? Ecological rationality, the term means it's the study of the conditions under which heuristics or other strategy are successful or not. And it is a follow-up from an analogy that Herbert Simon used, namely, he said that human rational behavior is like a pair of scissors, and whose two blades, cognition, heuristics, and the task environment, the world, you need to look at both of them to understand how a pair of scissors works. If you just look at one pair, what's in your mind, you're not understanding behavior. So most problems in behavioral economics and other parts of psychology come because people only think about the mind. So if a person is risk averse, if they're system one, or other, or personality traits, you will not understand behavior if you not at the same time look at the environment. And here, in this case, I'll show you. So ecological rationality is a study that's a mathematical study or a computer simulation. And the one result I show you now is, can we identify situations where a heuristic that relies on a single reason cannot be beaten by any linear model with the same reason and many more? Here is the answer, which can be intuitively understood. It's called the dominant Q conditions. So here you have a situation where 5 Qs or features are used to predict something, like whether a customer will buy again. And the weights here are like regression weights, beta weights. So the weight, this is the weight of the highest valid Q. And the weight is, the second weight is the additional contribution. And the third one is additional to the first Q and so on. So if the first weight is larger than the sum of all the others, as in the example, it's very clear that just relying on this one can never be changed by doing any kind of linear model of all of the other ones. So in this case, the heuristic is faster, is more frugal, and is also at least as accurate, and in the real world of uncertainty, it will be also more accurate, because then we also have estimation error. Here is another case for ecological rationality, we change now the problem. Now the problem is how to make an investment decision. So how do you have a sum of money, you have a number of assets, call it N, and you need to distribute your money on the assets. Harry Markowitz got his Nobel Memorial Prize for the solution of this problem, and it's the mean variance model. Those of you who have studied business or finance have been brought up with this model. I'm not going to explain it, but again, the problem is not calculating it, but estimating all these returns and the variances and the covariances. When Harry Markowitz made his own decision, putting his own money in for the time of his retirement, he used his Nobel Prize winning optimal solution. No, he did not. He relied on a simple heuristic that is known as 1 over n. So allocate your money equally to each of the n funds. If n equals 2, you do 50-50. If n equals 3, you do a third, and so on. Now, you can again see the difference between a heuristic, which is fast and frugal, in this case takes in no data, and an optimization model, which tries to estimate many, many parameters from the past. So in data fitting, if you fit already known data from the past, mean variance model will always win, but not in prediction. For instance, the study that's noted down here did 8 tests between mean variance and 1 over n, and found that in 7 out of 8, 1 over n made more money than mean variance as measured by Sharpe ratio and similar things. So again, the important question is, can we identify the situation where the simple heuristic does better than not? And here are general conditions. So on the left side, we have situations that are similar to risk. So there's low uncertainty, there are few alternatives, high amount of data. And here, complex situations generally pay. That's the world of optimizations of big data or mean variance in our example. On the other side, there's high uncertainty, there is many alternatives, small amount of data, and that's the world of simple solutions, heuristics such as 1 over n. For instance, the authors of this study I mentioned have tried to estimate how many years of stock data one would need in order so that 1 over n finally is being overtaken by mean variance. And the answer was, if n equals 50, so that means if there are 50 assets to invest in, then one would need 500 years of stock data. So in the year 2500, you can stop relying on simple heuristics and using the complex model if the same stocks are still around in the stock market in the first place. So I come now to my final point, and I call this psychological AI. So it is based on the insight that in situations under uncertainty, you need to make it simple, not too simple, as Einstein said, but you need to scale it down. And that was the original idea of Herbert Simon, namely to find out how experts deal with uncertainty and program this into software and then use it to make computers smart. That psychological AI had not worked as Simon thought, for beating the chess master. That was done by machine learning, which is blind with no theory and just computational power. But chess is a situation of an enormously stable world, and that it's not where psychological AI functions. The human brain evolved to deal with uncertainty, with a changing dynamic world, not with a stable world of calculable risk. So I will give you now 2 examples, one from a pandemic and the other one from our work with the Bank of England, that illustrate in both cases, we take what is known in psychology, how people deal with uncertain worlds, and then program it into software, and then make predictions. And I'll start with predicting the flu. As most of you will know, Google started in the year 2008 to make predictions about the flu-related doctor visits. And the idea was smart, namely, so people who have symptoms are likely to give in search terms that relate to the flu in order to find out what I should do. So the idea was one can very quickly and faster than the Center for Disease, the CDC, it can make predictions about the spread of the flu. And so what happened is it worked first, but then in 2009, the swine flu came. And the swine flu came out of the season, and big data had learned that the flu is high in the winter and low in the summer, when the swine flu came in the summer, so it failed. At this time, the Google engineers had to make a decision, namely, how to revise the algorithm that didn't work well. And again, there are two ways to go. One is, it's a complex problem, so make it more complex. And that's where they went. So the original algorithm was validated on some 50 million search terms, and millions of algorithms have been tried. And it had some 45 variables, predictors. And that was then changed into a more complex algorithm with 160 or so predictors. The exact number of predictors is secret, and so is the algorithm, and so is the kind of predictors. So what we did is, we started from psychology, not from data. We know from psychological research that people, the moment they are in a volatile environment where quick changes are possible, they do not rely on all the past experience or all the data they have for the last years, but they rely only on the most recent data. So we formulated a heuristic that's very similar to the one you have seen, a recency heuristic that predicts that the flu-related doctor visits next week will be the same as those last week and ignores everything else. So I'll show you now how this heuristic fares. So what you see here are the years 2007 till 2006, and this was the time when Google Flu Trends was terminated. And the black line are the actual flu-related doctor visits, and the recency heuristic is the blue line, and the red one, Google Flu Trends. So you can see here in the year 2007, when it started, the recency heuristic is basically, the blue line is on top of the black one, so you can hardly see them. And Google Flu Trends does quite well. It's a little bit low. And in the early 2008, it's a little bit below, yes. But if you now go down here and into 2009, you see that the red line is going down, just it did last year, because the big data algorithm thinks that this year will be like the last year's. And that was the swine flu, that belly. Yeah? The recency heuristic can easily follow up all the changes very quickly. It's too late a week, yes, that is error. And then here is where the Google engineers updated their algorithm, as I explained before. They tried to make it more complex. So the Chris Anderson, editor-in-chief of Wired, announced around this time that using big data and Google Flu Trends, that correlations supersedes causation and science can advance even without coherent model. And he asked, what can science learn from Google? Let me pose a different question. What can Google learn from science? And that's one thing that Google can learn from science. If you're dealing with uncertainty, make it simpler. But the Google engineers made it more complex here. And you can see that we have checked that it didn't make anything better, make it more complex. Here it started to overestimate, and here it ended up overestimating very highly, and at the end it was shut down. If you look at the entire time of 8 years, the error that Google Flu Trends made, that's on this scale here, is 0.38 percentage points. The reason the heuristic could reduce the error to almost half. This is an example for one data point can predict the flu better than big data. And the reason is because we have to do with a volatile world. Here I give you another example, and to my great pleasure, a group of economists have now realized about the power of simple heuristic, as we call them, fast and frugal heuristic. And this group of economists, including a Nobel laureate, Joseph Stiglitz, have tested exactly the same reasons as heuristic on a different problem, on predicting expectations in markets, demand expectations. And the conclusion was that in complex and changing macroeconomic environments, fast and frugal, robust heuristics may not be second best options as economists have believed, but rather rational responses. So my final example is about our work with the Bank of England, and I will use it to explain a different kind of heuristic. So one of the things that went wrong with the crisis were the algorithms being used. And predicting the financial world is most of the time predictions under uncertainty. And I'll invite you to read Andy Haldane, who is the the chief economist of the Bank of England, his article, The Dog and the Frisbee. The Dog and the Frisbee is named after the gaze heuristic I showed you at the beginning. That was the first heuristic explained him, and which he then used to go and give a Jackson Hole talk that was unheard of with this title and got the prize of the best speech for Wall Street Journal. So I'll show you one of the problems. The problem is how to predict which bank is volatile, that may fail and may need to be saved. Current models are highly complex, and we work with the Bank of England to construct fast and frugal tree. This is no longer a single reason heuristic. Here are three: the leverage ratio, market-based capital ratio, and loan-to-deposit ratio. I'm not going into details, but I want to briefly explain you how such trees are built. And they are built by a combination of expert knowledge or intuition and lots of data. So the reasons were extracted from the expert judgment of the economists on the Bank of England, the top. And they consider leverage ratio, market capital ratio, these are the most important reasons. The structure of the tree was our contribution. It's called a fast and frugal tree. It's an incomplete tree. And it's incomplete in order to avoid overfitting the data. And it has the following property. In the case of binary decisions as here, it has the number of exits. There's an exit after every question. And the total number is n, the number of questions, plus 1. And the values, the cutoff values, are then estimated again from data. So that's an interplay in that. So for instance, if this fast and frugal tree would have been used before 2008, UBS, one of the banks that had been saved, would have been immediately put in red flag because their leverage ratio were much smaller than this limit. Also note that the tree is not compensatory. You cannot make up, UBS would have met all other criteria, but not this one. So it's not compensatory. It's not like expected utility maximization. We always can make trade-offs. It's more like the human body. So if your heart fails, your vision and your lung doesn't help very much, even if it's good. So that's the idea. And that tree has been shown to be competitive with more complex models, and typically better, and also it's transparent. And that's an important advantage. So let me summarize. I was talking today about decision-making under uncertainty. And the important points are a situation of risk that is a stable world, where tomorrow is like yesterday, is very different from a situation of uncertainty. And the best decision under risk is not the best one under uncertainty. So Markowitz's model that is wonderful under risk, if the assumptions hold, is not the best one under uncertainty, and he himself didn't use it. Under uncertainty, smart heuristics can be faster and more accurate than complex analytics. I showed you a few examples, including machine learning. Intuition is the unconscious use of heuristics, a form of unconscious intelligence based on years of experience. And it can well combine with building models of heuristics. And finally, less can be more. Using less data and computation can actually lead to better predictions. I invite you to try this with your own data. Thank you for your attention.